Several approaches exist to define and discuss probability. Two of these methods are popular. One uses relative frequency definition of probability, and the second approach uses axiomatic definition. Prior to the introduction of the axioms of probability, it is necessary that we first develop certain elements of set theory. Probability definition. To each event defined on a sample space S, we shall assign a non-negative number called probability. Probability is therefore a function. It is a function of the events defined. Notations. P of A is the probability of the event A. When an event is explicitly stated as a set by using braces, we use the notation Axioms of Probability. The probability P of A of an event is a non-negative number assigned to this event. P of A is greater than or equal to 0. Probability of occurrence of sample space S is unity as S is an all-encompassing event. P of S is equal to 1. If A of M intersection A of N is equal to phi, for all M is not equal to N, is given as 1, 2, so on up to N, where N is possibly infinity. So for N events An, where N is equal to 1, 2, so on up to N, N could be infinity. Defined on sample space S having AM intersection An is equal to phi, for all M not equal to N is equal to 1, 2, so on up to N, then P of A union B is equal to P of A plus P of P. Mathematical model of an experiment. A real experiment is defined mathematically by three things: assignment of a sample space, definition of events of interest, making probability assignments to the events such that the axioms are satisfied. Establishing the correct model for an experiment is the single most difficult challenge in solving probability problems. Probability introduced through sets. The collection of all possible outcomes is called the sample space. A set of outcomes or subset of the sample space is called an event. The union A union B is equal to A plus B of two events A and B, where the event that occurs when A or B or both occur. The intersection A intersection B is equal to AB of the events A and B, the event that occurs when both A and B occur. The axiomatic approach is based on three postulates. The probability P of A of an event is an non-negative number assigned to this event. P of A is greater than or equal to 0. Probability of occurrence of sample space S is P of S is equal to 1. If the events A and B are mutually exclusive, then P of A union B is equal to P of A plus P of B. Probability as a relative frequency. Relative frequency. Assigning probabilities based on experimentation or historical data. The relative frequency definition is based on the definition that probability P of A of an event A is the limit P of A is equal to limit n tends to infinity n of A by n, where Na is the number of occurrences of A and n is the number of trials. In physical experiments, the values of Na and n may be large in number, but they are finite. Their ratio cannot therefore be equated even approximately to a limit. Example 1. Out of 1000 randomly selected consumers, 140 preferred brand X. The probability of randomly picking a person who prefers brand X is 140 by 1000, which is equal to 0.14 or 14%. Example 2. Corresponding to the graph, observe the relative frequency of corrupted pulses sent over a communications channel. Experiments and sample space. Probability is the chance that a particular outcome will be realized. A certain outcome has a probability ρ of 1.0. An uncertain outcome has a probability less than 1, that is, ρ is less than 1. If one outcome is uncertain, then there are at least two possible outcomes. The sum of the probabilities of all outcomes is equal to 1. That is, sigma of ρ is equal to 1. That is, one of them will occur. An experiment is any process of observation with an uncertain outcome. And the sample space is a list of all possible outcomes of a probability experiment. Sample space can be discrete or continuous. Discrete and continuous sample space. Finite sample spaces deal with discrete variables that can take on only certain values. For example, a whole number, that is, a count, or a qualitative category. Discrete variables contrast with continuous variables that can take on any one of an infinite number of possible values over an interval.
Categorical variables are necessarily discrete. Example, the variable color yellow, blue has events such as yellow, blue, or color equal to yellow, color equal to blue, or C equal to yellow, C equal to blue.
Discrete quantitative variables have only a finite or countable infinite set of values, usually counts. Example, x is equal to number of children in a family 0, 1, 2, so on, with events of interest such as x is equal to 0, x is equal to 1, x greater than 0, or x lies between 0 and 10. Continuous quantitative variables are uncountable infinite and can take on any value in an interval. Example, y is equal to age in years, w is equal to weight in grams. Events of interest are always intervals. Example, y is less than 17.5, or y lies between 17.5 and 21.5, or y is greater than 21.5. Singleton events such as y is equal to 17.5 and y is equal to 21.5 are never of interest because continuous variables are always rounded off. Continuous sample space contain an uncountable infinite number of events.
The model continuous probability distributions are used by density curves. The imaginable shapes of density curves are
Figure shows a continuous sample space. Events are defined over intervals of values. Probabilities are computed as areas under the corresponding density curve. The total area under a density curve represents the whole population or sample space and equals 1. Events. An event is defined as a subset of the sample space. Because an event is a set, all the earlier definitions and operations available to sets will apply to events. Example, if two events have no common outcomes, they are mutually exclusive. As with the sample, events may be either discrete or continuous. Events defined on continuous sample spaces are usually continuous. In the experiment, choose randomly a number from 6 to 13. The sample space is S is equal to S lies between 6 and 13. Discrete events may also be defined on continuous sample spaces. An example of such an event is A is equal to 6.13225 for sample space S is equal to S lies between 6 and 13, or S is greater than or equal to 6 and less than or equal to 13. Different types of events are sure event. The sample space S of an experiment is the set of all possible outcomes. Therefore, the event represented by S is a sure event. Impossible event. An empty set phi is always a subset of a set S. Hence, the empty set phi can always be considered as representing an event of an experiment. Thus, it is an impossible event. Equally likely events. Let S be the sample space of a random experiment. If all the elementary events of S have the same chance of occurring, then the events are said to be equally likely events. Mutually exclusive events. When one event occurs, the other event cannot occur, or the two events cannot occur together. Mutually exhaustive events. Let S be the sample space and A1, A2, A3 so on up to Am be the events defined on this sample space. If A1 union A2 union A3 so on up to union Am is equal to S, then the events are said to be exhaustive. Combination of events. A union B means either A or B or both. A intersection B. Both A and B must occur. A bar, not A. A minus B. A but not B. A intersection B is equal to phi. Mutually exclusive events A and B. Combination of events. Observe A union B, that is, either A or B or both. This is the representation of A union B. A intersection B. Both A and B must occur. This representation shows A intersection B. A bar, not A. This representation shows A complementary representation. A minus B. A but not B. This representation shows the representation of A minus B. A intersection B is equal to phi. Mutually exclusive events A and B. This representation shows what mutually exclusive events mean. Joint probability. The probability P of A intersection B is called the joint probability for two events A and B which intersect in the sample space. A study of a Venn diagram will show that P of A intersection B is given as P of A plus P of B minus P of A intersection B. Equivalently, P of A union B is equal to P of A plus P of B minus P of A union B, which is less than or equal to P of A plus P of B. In other words, the probability of the union of two events never exceeds the sum of even probabilities. The equality holds good only for mutually exclusive events because A intersection B is equal to phi, and therefore P of A intersection B is equal to P of phi is equal to 0. To find the probability of random events, say A, under condition that the random event, say B, has occurred, this changed probability is called conditional probability of A when B has occurred, denoted by P of A by B. Given some event B with non-zero probability, P of B is greater than 0, we define the conditional probability of an event A given B by P of A by B is equal to P of A intersection B by P of B. The conditional probability P of A by B simply reflects the fact that the probability of an event A may depend on a second event B. Conditional probability is a defined quantity and cannot be proven. The conditional probability must satisfy three axioms.
Axiom 1. P is greater than or equal to 0.
Obviously satisfies axiom 1 by its definition because P of A intersection B and P of B are non-negative numbers.
Axiom 2. P of S equal to 0.
The second axiom is shown to be satisfying by letting S is equal to A.
P of S by B equal to P of S intersection B by P of B, and it is equal to P of B by P of B is equal to 1. Axiom 3. P of A union B is equal to P of A plus P of B if P of A intersection B is 0.
This axiom may be shown to hold by considering the union of A with an event C. A and C are mutually exclusive. If P of A union C of B is equal to P of A given B plus P of C given B is true, then axioms 3 holds good.
Proof is as follows.
Independent events. Two events A and B are said to be independent if the probability of occurrence of A does not depend on occurrence or non-occurrence of event B. Conditional probability P of A by B in this case can be written as P of A, that is, P of A by B is equal to P of A, or P of B by A is equal to P of B. Substituting, we get P of A intersection B is equal to P of A by B into P of B, which is P of A into P of B. So, condition to be satisfied for two events to be independent is P of A intersection B is equal to P of A into P of B. Note, if events A and B are independent, then A dash and B dash are also independent. Hence, P of A dash intersection B dash is equal to P of A union B whole dash is equal to 1 minus P of A union B. On simplification, we will get them to be P of A dash into P of B dash. Hence, A dash and B dash are also independent events. For three independent events, P of A1 intersection A2 intersection A3 is given as P of A1 into P of A2 into P of A3. Likewise, for n independent events, P of A1 intersection A2 intersection A3 intersection so on up to An is given as P of A1 into P of A2 into P of A3 so on up to P of An. Total probability. The probability P of A of any event A defined on a sample space S can be expressed in terms of condition probabilities. Suppose we are given n mutually exclusive events Bn, where n is equal to 1, 2, so on up to capital N. These events satisfy Bm intersection Bn is equal to phi, where m is not equal to n. And we shall prove that probability of A is equal to sigma n runs from 0 to n probability of A by Bn into probability of Bn, which is known as total probability of event A. Here is the proof of the conditional probability that we have just seen. Bayes' theorem. The definition of conditional probability as given by P of A by B. Bayes' theorem. The definition of conditional probability as given by P of A by B is equal to P of A intersection B by P of B applies to any two events. In particular, let Bn be one of the events defined above in the subsection on total probability. Equation P of A by B is equal to P of A intersection B by P of B can be written as P of Bn by A, which is equal to P of Bn intersection A by P of A. If P of A is not equal to 0, or alternatively P of A by Bn is equal to P of A intersection Bn by P of Bn if P of B is not equal to 0. One form of Bayes' theorem is obtained by equating these two expressions. P of Bn by A is equal to P of A by Bn into P of Bn by P of A. Another form derives from a substitution of P of A is equal to sigma n runs from 1 to A, P of A by Bn into P of Bn. P of Bn by A is equal to P of A by Bn into P of Bn by P of A by B1 into P of B1 plus P of A by B2 into P of B2, so on up to P of A by Bn into P of Bn, where n is equal to 1, 2, so on up to n.